to talk about counting in the first place is actually to lead to complexity. Complexity is what we care about. Now, what is complexity? Complexity itself is a way for us to characterize the difficulty of a problem as well as the performance of an algorithm. Now, what do we actually mean? Now, we want to have an algorithm that what we call efficient. Efficient means that it uses as little resources as possible, because when it uses little resources, it means that you're going to save on time as well as on the computational resources that you need, which means that you can solve bigger problems or you can solve problems more efficiently. Now, one of the topics that we're going to talk about shortly is what we call big O notation. This is going to be a notation that you will see frequently in many references when people talk about algorithms, because this is something that indicates the level of complexity that an algorithm has. Now, what is complexity? So just now, Kashan and Wei Ming, so they talk about this genetic algorithm as being an optimization problem. So one of the problems that they mentioned is this idea of trivial Salesman problem, which is that how do you figure out what is going to be a route that visits a certain number of cities, and you want to minimize the distance. Now, this is actually a very common problem. You face this problem frequently. So of course, if you're an actually traveling salesman, right, but you may not be one. But for example, logistic companies like DHL, FedEx, and so on, they do delivery every day. And in their delivery, they will have some kind of schedule, because then they will figure out what is going to be the most efficient way for them to go to the different places that they need to deliver to. Now, in this problem, you need to determine what is going to be the sequence of doing something. Now, this is one of the problems that we consider very complex. Now, for example, right, so this is an example from the Winter Olympics that is going to come up, right? So this is going to happen in Korea. And there is always a tradition for Olympics where they carry the torch, right? So the torch relay, they go from one city to another city to another city. They pass on the things from one athlete to another athlete until they complete a certain route. And I think part of the thing is to try to publicize this Olympic event to as many people as possible. Now, they need to solve that problem where they need to figure out what is going to be the route they're going to take. Now, if we define a problem to be the optimal route, which could be anything, it could be like the shortest distance, for example, then to look through all the possible answers, you will actually have to go through 80 factorial, which is a very big number of permutations. Now, even if you have a very fast computer that can look through every one of them, you still need to have, in the order of 10 to the 100 centuries, which means that practically it's not, possible, right? We don't have the time to wait for such a thing. And the Olympics happen every 4 years, right? So they can't wait that long to finally find an answer. So now, in that sense, what we are talking about here is the notion of complexity. Complexity can be defined in terms of how many operations you will need to solve a particular problem. Now, why do we need to understand complexity? Is because most of the time we need to compare algorithms. Now, let's then get talking about algorithms. Now, algorithm is described by a few things, but essentially it's a way to solve a problem in terms of a number of steps. So you have an input, you have an output, and then you have a sequence of operations to actually solve it. Now, given the same input, given the same output, you can have different algorithms, which means that you can have different operations to solve them. Now, so meaning that if you have a particular problem, you start from input, you want to end up in the output, then you want to be searching for what algorithm you need to use to solve the problem. So, and frequently, there are actually more than one algorithm that can come into the picture. So meaning that if you want to solve a problem, usually there are many ways to solve it. Now, if there are many ways to solve it, then you want to find the best way. So that's when we get into a discussion of how do we make comparisons between algorithms and what does it mean to have the best algorithm. And so let's take a look at an example, right? So this is, this is a mathematical problem that I think most of us have come across early on. So the idea of the greatest common divisor is to find a number that can divide two numbers, and you want to find the largest such number. So for example, so if you have 4 and 8, right? What is going to be the number that can divide both of them? 4 and 8. What is the largest number that can divide both of them?
4.
4, right? Yes. How about 81, 36? 9, right? Okay, so how about 1989, 867? Did you figure it out? Now, to figure it out, we basically need an algorithm. An algorithm is going to be a series of steps that we're going to do to solve a particular problem. And we're going to look at a couple of them. Now, the first algorithm is what we call brute force. This is an algorithm that is always available to you, meaning that if you have a computer, you can always try the brute force method, which is to try every possible method. Now, but of course, we try the reasonable ones, right? So let's see. So let's assume that we are trying to solve the problem for 81 and 36. And we are trying to find the largest number that can divide both 81 and 36. So the reasonable starting point is to try the largest possible number, which in this case, it should be 36, right? Because any number that is larger than 36 wouldn't divide 36 itself. So then you try 36. Now, can 36 divide 81? No, right? So then the answer cannot be 36. So then you move on to the next possible choice, which in this case, smaller than 36 is 35. So you can try, does 35 divide 81? No, right? So you go to 34, 33, 32, all the way down to until you actually find an answer. And the answer will be 9. And because you're looking for the largest one, and you start from big to small, the first number you find will be the largest one that can divide both of them. Now, if you do this, then the algorithm has to execute 28 times in terms of trying to, different numbers that it will try. So from 36 to 9, it will take 28 possible tries before we find that the answer is 9. Now, second algorithm, which is called Dijkstra's algorithm, this algorithm is going to make use of a particular principle. And the principle is that if you want to find a number that divides A and B, that same number should also be able to divide A minus B, which means the difference. Now, meaning that, for example, if you want to find a number that can divide A and B, because then the difference between A and B itself must be divisible by that number. So an example of this, for instance, 81, 36. So you want to find a number that divides both 81 and 36. So that same number should divide the difference between them, which is 45. So then you have transformed 81, 36 to a smaller problem, which is 45 to 36. And then you transform it again into a smaller problem, 936, 927, 918, and finally you get 9 and 9. In that sense, you cannot get any smaller than that. You have already found the answer. Now, how many steps do you take? In this case, you only take 5 tries. Now, the problem gets smaller and smaller, much faster, so you need to do 5 tries. Now, what it means is that the same problem, which is to find the greatest common divisor, you may have different algorithms, but the different algorithms is going to require different number of times to actually solve the problem. And the important thing is that the difference between them is actually going to get larger as the input size actually gets larger. So meaning that if you chance upon a good algorithm, you're going to save a lot more time, even as your input size actually keeps growing. And that's why we care about complexity, because we want to minimize the number of operations that we are going to try to solve. Now, so when we compare algorithm, first we need to make sure that it's correct. Okay, so if the algorithm is not correct, then it doesn't matter if it is efficient, right? So why do you want to get a wrong answer fast? I mean, it doesn't actually help you. Now, once you have made sure that the algorithm is correct, then we can talk about efficiency. Now, being efficient, meaning that we're going to use as little resources as possible, which could be time, which could be space. Both are important resources for computers. We're going to focus in terms of time in this course. Most of the time, that is the thing that is limited. So space, you have to buy more memory, you need to buy more hard drive, and that's going to affect the amount of space that you have. The concepts are very similar. So if you can reason with it in terms of time, you can also reason with it in terms of space. Now, but there are some things that we're going to clarify, like this is not relevant to the problem at hand. So remember that what we want to do is to characterize an algorithm. So what we are concerned with is the algorithm itself. So sometimes you may find that some program runs faster or slower, but it may be due to different reasons. And these other reasons are not relevant to the discussion at hand. Now, for example, what programming language it is, right? So C++ or Java. Now, in effect, there is a difference. So meaning when you write your code in terms of C++ or Java, there could be a real difference in terms of speed. But that difference in terms of speed, it doesn't depend on the algorithm. It usually depends on the fact that some languages are closer to the hardware. So then they can be optimized much easier. But in terms of an algorithm, you can always write it in any programming language you want. Now, for instance, like in this course, we use Python. But it doesn't mean that what you learn is only relevant to Python. In fact, you actually can write the same algorithm in any language. So if one language is faster than another one, you just write it in the language that is faster. Now, what is the operating system? It doesn't matter because any algorithm can run on any operating system. So if one OS is faster, you just run it on that OS. Now, the processor speed also doesn't matter. Of course, the processor speed is faster is going to make your algorithm run faster, but it's not a property of the algorithm, it's a property of the computer. The same thing in terms of who implemented it or how much data you use, because these are outside of the algorithm. You can always get the best person to implement it, or you can always use the same amount of data. So that doesn't affect the quality of the algorithm. The quality of the algorithm depends only on the number of operations that it takes to solve the problem. Now, let's take a look at an example, right? So here, you may be given a simple algorithm that tries to find the largest number within an array. Now, then you first design an algorithm, and this algorithm is actually very simple. So this is to go into a loop that goes from 1 to n minus 1, and each time, right, so you keep the maximum number in an array. At first it's the first number, and then you're going to look through the array to see whether any number is larger than that. If it is larger, then you replace it. So by the time you get to the end of the array, then you will get the largest number. Now, then we start counting in terms of the operations. What are operations that we are counting? We are counting the basic operations. These are things like addition, subtraction, multiplication, division, assignment, comparison, the Boolean operator, like for example, like a not or other things like that. Now, in this particular case, if you look at the operations they do, essentially there is comparison and there is assignment. So then we're going to count these things. So this is where the counting concepts that we learned earlier is going to come into the picture. Because sometimes to count how many times an algorithm runs, we need to figure out what is going to be the application of product rule, sum rule, permutation, combination, and so on. Now, for this example, the number comparison is going to be n minus 1. Because if the length of this array is n, then it's going to go inside this loop exactly n minus 1 times. And every time you go inside this loop, you're going to execute this if condition, which does one comparison. So the number of times it goes into the loop is going to be n minus 1. Now the number of assignment is going to be at most n. So why is it at most n? Well, it's going to go into the loop n minus 1 time, but it doesn't always meet the condition of the if, right? So sometimes it does, sometimes it doesn't. So even if it does all the time, then it's just going to be n minus 1, but there is another 1 here. So n minus 1 plus 1 is going to be n. So that is what we are trying to do. So when we get an algorithm, we try to analyze how many times it's going to run for an input size n. Then we try to formulate it in terms of a function, and there's a function that we are going to analyze. Now, before we actually talk about how to do the complexity of a particular algorithm, we're going to spend a bit of time to try to do this counting problem. Now, here you're given two problems, but to make it simpler, we're going to give you the algorithm. So there is one algorithm on the left, which is to find the largest number in the first 10. And there's going to be another number on the right, another algorithm on the right, which is to try to find the smallest difference within any two numbers. So try to figure out how many operations you're going to need to solve each of these problems. Then about 10 minutes time, we're going to come together and discuss these things.